Hello friends, Namaste. My name is Dr. Sachin Borse. I am Professor and Coordinator International Relations, Imperial College of Engineering and Research, Pune, India. Today I will discuss the interesting topic, a boundary layer. So let us move to the topic, boundary layer. Now let us understand what is boundary layer. So boundary layer is a thin layer. It is a thin layer of the fluid adjacent to the solid body where there exists a velocity gradient, and because of this velocity gradient there exists the shear stresses. We know this from the Newton's law of viscosity. If you see the Newton's law of viscosity, it depends, shear stress depends on mu viscosity and du by dy, that is the shear strain. So as long as there is a velocity gradient and viscosity, there will be shear stress. So inside the boundary layer there is the velocity gradient, and because of this velocity gradient there are the shear stresses. So if you move, if you see the diagram here, the velocity on the wall or the body surface, solid surface, is 0. That is called as no slip condition. Then velocity goes on increasing till it reaches to the free stream value or the inlet value. The relative velocity of the fluid at the wall is 0. That is called as no slip condition. If we go beyond the boundary layer, you will find that the velocity gradient is negligible, and if you see from the Newton's law of viscosity, you will find that hence the shear stresses are negligible in this area. So we can treat it as good as invisible flow without viscosity. Now along the length also, if you go along the length, the velocity gradient is also 0 or negligible, and therefore the shear stresses. So now we will see the different regions in the boundary layer. On the unlike the flow in the pipe, where either there exists a laminar flow in the tube or pipe, or there exists the turbulent flow. But in case of the flow over the surface of the body, initially in the initial length of the body there exists the laminar flow, then it transits, and then it goes to the, in the later length it goes to the turbulent range, or it becomes turbulent. So if you see this diagram at the starting, from when the flow is coming from the left hand side with the free stream velocity u infinity first, then boundary layer start growing, its thickness goes on increasing. First it becomes laminar, and at xc it start to begin turbulent. The point where it starts to become turbulent is critical Reynolds number, and this critical Reynolds number is of the order 5 unit 10 raised to 5. Then it becomes initial in transition, it goes in transition, then it becomes turbulent. If you see the turbulent boundary layer, just near the wall there is one region called as laminar sublayer. So here the flow behaves like a laminar, so it is called as the laminar sublayer, and thereafter it becomes turbulent. In between the fully turbulent and a laminar sublayer there is a buffer layer. So for the flow on the surface, external flow over the surface, initially it becomes a laminar boundary layer, then in a later length it becomes transition, and then to the turbulent boundary layer. So all this exists on the same surface. So here the Reynolds number is specified based on its location from the leading edge. Okay, so we calculate distance x from the leading edge at any given point. Suppose at point xc, if I calculate Reynolds number, it will be rho u infinity xc by mu. Okay, so this way we calculate the Reynolds number. So Reynolds number at each point goes on changing from leading edge towards the right hand side at the end, that is called as trailing edge. So at the leading edge Reynolds number is 0, then it goes on increasing based on the x location of that point on the surface. Okay. So the Reynolds number where it starts converting from laminar to the turbulent is called as critical Reynolds number, and typically this critical Reynolds number is 5 into 10 raised to 5. In the study of the flow over the immersed bodies, our attention is mostly on the boundary layer. Why? Because in this boundary layer there exists a velocity gradient, and velocity gradient gives rise to what is called as a shear stress. We know the Newton's law of viscosity. Shear stress is mu du by dy. So shear stress will exist if there is du by dy, velocity gradient, or viscosity. If either of these two is absent, there will not be any shear stress. In this boundary layer there exists a velocity gradient, and it is a fluid having this viscosity. The shear stress is obvious, but beyond this the velocity gradient outside the boundary layer is negligible. So our attention is on the boundary layer to find the shear stress, and from the shear stress to find the shear force that will give us the drag force. So let us understand one concept called as boundary layer thickness. It is basically given by the letter delta. It is the distance from the surface where the surface of the wall where the fluid velocity becomes 99% of the free stream velocity. Either we can say 99%, or we can say 0.99 times the free stream velocity. That thickness, it is the imaginary thickness. It is imaginary, we cannot see this. So this distance is called as boundary layer thickness. Now let us see how the velocity changes at the laminar boundary layer and the turbulent boundary layer. Now if you see the graph here on the x-axis, it is the distance divided by, it is a normalized distance from the wall divided by the boundary layer thickness. On the x-axis, local velocity divided by free stream velocity. If you see the laminar boundary layer, so when you take change of velocity divided by y, you will find that for the laminar flow, laminar boundary layer, the velocity gradient is less as compared to the turbulent boundary layer, where the velocity gradient is large. And we can say that shear stress in case of laminar boundary layer is less than shear stress in the turbulent boundary layer. Now we'll understand how the boundary layer thickness goes on increasing, how what parameters affect the boundary layer growth. First parameter is the distance from the leading edge, that is the x. More we move away from the leading edge, more will be thickness of the boundary layer. Second thing, free stream velocity u infinity. If the free stream velocity increases, boundary layer decreases, and vice versa. So if the free stream velocity decreases, boundary layer thickness will increase. Next parameter, viscosity of the fluid, that is the mu. So if more is viscosity of the boundary layer fluid, more will be the thickness of the boundary layer. Next parameter, density of the fluid, rho. Lower the density of the fluid, more is the boundary layer thickness. Or we can say, more the density of the fluid, less is the boundary layer thickness. So only we can say for u infinity and rho it is inversely proportional, and for x and mu it we can say it is directly proportional. Now let us concentrate on a topic called as the separation of the boundary layer. It is a very important point, because when there is a flow separation, it leads to cause additional drag on the system, as well as it will reduce the lift force on the wing. So it is essential to understand the boundary layer separation. Now let us see that there is a converging diverging passage. So on the left hand side it is a converging passage, and on the right hand side it is a diverging passage. Now if you see converging passage means what is happening to area, it is negative. There is area goes on decreasing, and because of this decrease in area, the velocity goes on increasing, and from the Bernoulli's theorem, the pressure will go on increasing. It will go on velocity will increase. So what will happen to the pressure? As per the Bernoulli's theorem, it will go on decreasing. So the pressure on upstream side is greater than pressure on the downstream side. So direction of the flow is from upstream to downstream, as well as pressure is high on the upstream side and pressure is low on downstream side. So both are favorable condition. Okay, so this is, we can say it is a converging passage. Then you move to the diverging passage. In the diverging passage, what happens? The area, change of area is positive. Area goes on increasing. With the area goes on increasing, the velocity will go on decreasing. So as velocity is decreased, from Bernoulli's theorem, pressure will increase. It means that downstream side pressure is higher and upstream side pressure is lower. So it is opposite. Pressure, higher pressure is opposite to the direction of the flow. So it is the adverse pressure gradient. And because of this adverse pressure gradient, the fluid near the wall will get decelerated, and there will come a point where there will be start of the flow separation. It is shown at the point 3. After the start of flow separation, further there will be flow separation, and because of this flow separation, there will be additional drag or reduction of the lift force. Now let us again go back to the converging section. What is happening? Again explaining this. In converging section, dA is negative, means area is going on decreasing. So what is happening to the velocity? Velocity is increasing. As per Bernoulli's theorem, pressure will decrease. So upstream pressure is higher and downstream pressure is lower. So we know that the flow should always take from higher pressure to lower pressure. So it is the favorable pressure gradient, and therefore there are no chances of the flow separation in the converging section. In the converging section, pressure, upstream pressure is less and downstream pressure is greater. So if you see always that du by dy in vertical direction near the wall is positive. So velocity is positive. Change of velocity, if you go from or just away from the wall, it is positive. So du by dy is positive. So there is no flow separation, and boundary layer is attached to the wall. So in this converging passage, there is no question of flow separation. Now let us move to the diverging section. In the diverging section, what is happening? Area is increasing. dA is greater than 0. Area is increasing. What will happen to the velocity? From the continuity equation, velocity will reduce as velocity is reducing from Bernoulli's theorem. Pressure will go on increasing. It means that your downstream pressure is greater. than upstream pressure. Okay, so downstream pressure is bigger, upstream pressure is lesser. So this, the opposite net force by this pressure will decelerate. It will decelerate the flow near the wall, and it will decelerate the flow, and the point will come, like point 3 will come, where it will start separating. Okay, so when the flow starts separating, du by dy at wall will become 0. After that, it will start separating. So this occurs in the adverse pressure gradient as the net pressure force opposes the motion of the fluid near the wall, and in the separated flow region the flow get reversed. That's why we get du by dy at a wall as negative, less than 0. So as I mentioned, flow separation is a bad effect in the fluid mechanics, and care should be taken to avoid this, because it increases drag and reduces lift force. So as this flow separation is undesirable, causes the increase in drag or decrease in the lift force, we need to control this. So now we'll see how to control the flow separation. First is to design the body to match the streamlines. Are you aware about the streamlines? Streamlines are imaginary lines, and they are in a such way that flow will not cross the streamline. So when you plot streamlines in the CFD, and if you see the absence of the streamline in particular area, and there is existing the gap between your body and the streamline, then you have to match your body shape to the streamline. If you do this, you can avoid the flow separation, and we can say flow separation, or there is boundary layer suppression. So that is streamlining the body. This is the first way to avoid or shift the location of the flow separation more towards the downstream side. Second way is to provide artificial roughness, like in the golf ball. Artificial roughness is provided to convert the laminar boundary layer to turbulent boundary layer, and to shift the point of the flow separation more towards the downstream side. Next is to provide the slot near the leading edge. You can see in the left side figure, the air is coming from the slot. It is giving some kinetic energy to the slowing down lower portion of the boundary layer. So because of this, fluid will remain attached to the boundary layer. It will have this kinetic energy. Next is providing the suction slot. The retarded fluid is sucked to the suction slot, so that the layer above the retarded or slow or fluid layer, which will have more velocity, will come in contact with the wall, and it will delay the boundary layer separation. Next one is blowing the fluid. So we can blow the air in the boundary layer, so that It can give the energy to the retarded fluid, and it can avoid the boundary layer separation. So these are all the methods that generally adopted to avoid the flow separation. Hello friends, now we will see the governing equation for the boundary layer. Now we know that what are the governing equation for the fluid mechanics. One is continuity equation and momentum equation. So there will be one continuity equation and there will be three momentum equation. So momentum equation is a consequence of the Newton's second law of the motion, that is mass into acceleration is the summation of the forces. So why there are three momentum equation? Because the force is a vector quantity and we need to describe the force in the x direction, y direction and the z direction. Now if you see the boundary layer, it is basically a two-dimensional phenomenon, and along the z the phenomenon variation is negligible, so basically it is a two-dimensional flow. Now again in governing equation, if you consider incompressible flow and two-dimensional flow, then we get the equation. One is continuity equation and two momentum equation in x and the y direction. X is along the length and y is perpendicular to that. Now boundary layer theory simplifies this governing equations. Now how we simplify this equation, let us see. So if you see the boundary layer, it is already described that boundary layer is very small as compared to the length of the plate. So you can see that for the small thickness, the variation of pressure across the boundary layer is very small. So we can say dp by dy is equals to 0, and also as boundary layer thickness is very small, we can say the pressure in the boundary layer is same as whatever the pressure just outside that. So we can say along the length dp by dx, pressure gradient along the length is dp infinity by dx, means whatever is pressure gradient outside the boundary layer, it is same. So u is varying perpendicular to the plate across the thickness of the boundary layer, but its variation along the length is small. Del u by del x is small, but if you take the derivative of del u by del x, it will become very small. It will become very small. When it is a very small, we can say it is a negligible. So del square u by del x square is 0. Now again the velocity component in y direction is very small. Basically flow is going in the x direction, so component of the velocity in the y direction is negligible. So we get del v by del x is 0, because along the length the v is very small, the variation of v is very small, but negligible. So we get del v by del x is 0, because along the length the v is very small, the variation of V is very small, but variation of V perpendicular to the plate is small, but it is not small. It is not very small. It is a small, and we know that V is small. Del V by del Y is small, so multiplication is very small. So it is negligible. Again, del V by del X, second derivative small, becomes very small, so it is negligible. We can say 0. Again, del square V by del Y, it is small, and second derivative of this is very small, so we can neglect this by putting these values. This 3 equation becomes 2 equation. So equation 3 vanishes, so we get basically equation 1 and equation 2. And in equation 2, del square U by del X square becomes 0, so we get this equation. So basically we get only one momentum equation. So how to solve this momentum equation? So there are 2 methods. One is exact method by Blasius. It is also called as Blasius similarity method. This is exact method. And another method is momentum integral method, which is approximate. Now here we'll see the momentum integral equation. Momentum integral equation, which is approximate. So what we do here? So 2-dimension incompressible boundary layer equation, which was simplified, is integrated here. It is integrated over the boundary layer thickness. So once we integrate this, we get one equation called as a von Karman integral equation, d by dx 0 to delta u by u infinity 1 minus u by u infinity, dy equals to 0 to delta 1 by rho dp infinity by dx dy plus tau w rho u square infinity. For the plate, this von Karman integral equation becomes where the pressure variation becomes 0, as it is not converging, not diverging. Okay, so we get basically von Karman equation as d by dx integration from 0 to delta u by u infinity 1 minus u infinity into dy is equals to tau w rho u infinity square. So this is the equation what we got. This is called as momentum integral equation for the flat plate. This is the equation number 4. Now to solve this equation number 4, we need the knowledge of velocity profile, that is the u by u infinity. Now what we do is we assume some profile, like we assume the cubic polynomial. If we assume the cubic polynomial velocity profile, for example, you can see u by u infinity is equal to c0 plus c1 y by delta plus c2 y by delta square plus c3 y by delta cube. So we assume this velocity profile. Now we can get c0, c1, c2, c3 based on the boundary condition we apply to the equation. Once we apply the boundary condition, then this velocity distribution becomes u by u infinity is equals to 3 by 2 y by delta minus 1 by 2 into y by delta cube. This is the equation 5. Now what we'll do, we will put this velocity profile in the von Karman equation. Putting the equation 5 in the von Karman equation, then we get, after doing the mathematical treatment, we get equation for boundary layer thickness as delta by x is equals to 4.64 divided by RE, square root of RE, where RE is local Reynolds number. It is rho u infinity x by mu. So we can see that the boundary layer thickness is proportional to the square root of the x. So please understand what we are seeing. The boundary layer here is the laminar boundary layer. Similarly, we can prove that shear stress tau w is equal to 0.323 rho u infinity square divided by square root of RE. So in short, shear stress is inversely proportional to the square root of the x. X is the distance of that point from the leading edge. Similarly, we can find the skin friction coefficient CF is equals to tau w by half rho u infinity square. So skin friction coefficient becomes, after putting the value, CF, it becomes 0.646 divided by square root of RE. So in short, the skin friction coefficient is inversely proportional to the square root of the x. So this is the local skin friction. For finding the average skin friction over the length, that is the CFL is equals to 1.292 square root of REL, where Reynolds number is rho u infinity capital L divided by mu. So here we conclude that the average skin friction is twice the local skin friction for the laminar boundary layer. Now whatever is skin friction coefficient, it is the same, we call it as a drag coefficient. So basically the value of drag coefficient will be 1.292 divided by square root of REL. So how we define the drag coefficient? Drag force divided by half rho a v square, where v is u infinity here. So this is about drag coefficient for laminar flow. Now I'll move to the turbulent boundary layer profile. So basically the turbulent boundary layer profile is logarithmic. If you see the velocity profile, so it is u by u infinity is given by y by delta raised to 1 by n, where n is 7 if Reynolds number is the less than 10 raised to 7, and if it is between 10 raised to 7 to the 10 raised to 8, if the Reynolds number is between 10 raised to 7 to 10 raised to 8, it is n is 8. If Reynolds number is between 10 raised to 8 to 10 raised to 9, n is equals to 9. So here in turbulent boundary layer, the boundary layer thickness is given by delta by x is equals to 0.37 RE raised to 1 by 5. So here delta is proportional to the x raised to 4 by 5. So x raised to 4 by 5 means what? Delta is proportional to x raised to 0.8. In the laminar flow, delta is proportional to the x raised to 0.5, but here delta is proportional to the x raised to 0.8. So the growth of the boundary layer is faster in the turbulent boundary layer. Skin friction coefficient. So here skin friction coefficient is proportional to 1 by x raised to 1 by 5. Similarly, drag coefficient, we can say it is given by total drag coefficient is CD is given by 0.072 RE raised to 1 by 5. So the obvious question that will come in the mind, how to find the total drag force on the plate. So what we have to do is we have to find the drag force that will come in the mind, how to find the total drag force on the plate. So what we have to do is we have to find the drag force because of the laminar boundary layer, and then we have to add the drag force because of turbulent boundary layer, then we can get the total drag because of both boundary layers. So let us see the difference between the laminar boundary layer and turbulent boundary layer. In the laminar boundary layer thickness delta is proportional to x raised to 0.5, and in case of turbulent boundary layer, delta is proportional to the 4 by 5, x raised to 4 by 5. Delta is proportional to the x raised to 4 by 5, that is a 0.8. Delta is proportional to the x raised to 0.8. So boundary layer growth is faster in the turbulent boundary layer. Now compare the shear stress. Shear stress is proportional to the x raised to 0.5. Shear stress is inversely proportional to x raised to 0.5, whereas in the turbulent flow shear stress is proportional to inversely proportional to. In the turbulent boundary layer, shear stress is inversely proportional to the x raised to 0.2. So we can see that shear stress is more in the turbulent boundary layer as compared to the laminar boundary layer. Now we will see one important concept that is called as displacement thickness. It is given by delta del star. So it is the distance by which boundary layer will be displaced in a frictionless flow to give the same mass flow rate as that with the boundary layer flow. So what is happening because of viscosity near the wall, the velocity is 0 on the wall, and then it is gradually goes on decreasing. So you can see average velocity in the boundary layer is less than what is beyond the boundary layer. Now somewhat it is blocking the flow, and how to take care, how to know this, how much it has blocked the flow. What we concept we use is the displacement thickness, and we just say that frictionless flow or invisible flow, we know that beyond the boundary layer the flow is there, and there is no we can say the velocity gradient is very less, and but viscosity is there, but the net effect is shear stress is negligible. So as if the flow is inviscid. So what we say that as if we are in the inviscid flow, and how much, by how much thickness it is blocking the flow, such that we get the same flow as we are getting with the boundary layer. That is called as displacement thickness del star. So it is shown in the diagram. Now there is equation to calculate the displacement thickness. Del star is given by integration from 0 to delta 1 by 1 minus u by u infinity dy. From this equation we can find the del star. So in this equation the value of velocity profile will be given in terms of y by delta. Y is the distance from the wall, and delta is the thickness, boundary layer thickness. From example, so in one example it is given that u by u infinity is equals to y by delta. Then just you put the in the place of u by u infinity, put the y by delta, and then integrate. You will get the delta star, that is the displacement thickness. And at the end, what will give, by putting this at the end, you will get the relation between the delta star and delta. So such problems are asked in the exam. Now I'll move to the next definition, that is displacement thickness. Now the distance by which will move the boundary from bottom to the top. How we are moving the boundary from bottom to the top? This it is creating blockage. By distance, the wall will shift upward to in the inviscid flow. We are seeing the above, after displacing, whatever is flow above the wall will be inviscid flow, the distance through which the wall will displace upward. To compensate the reduction of momentum due to the presence of boundary layer, so that is called as displacement thickness theta. It is indicated by the theta. So to compensate loss, we are moving the boundary layer wall in the inviscid flow. So by how much distance we are displacing our boundary wall, that is to compensate the loss of momentum, or to have the same momentum in boundary layer and same momentum in the inviscid flow. So we get the equation for theta, momentum thickness, 0 to delta 1 minus u by u infinity into the dy. That is the momentum thickness. Now we'll move to the energy thickness. Energy thickness is given by delta star star. So it is the same way. So as if we are replacing boundary layer by inviscid flow. To have the same kinetic energy, how much distance will move the wall from bottoms toward the top for the inviscid flow? That is the energy thickness. It is indicated by delta star star. So delta star star is given by equation 0 to delta 1 minus u square divided by u square infinity into bracket u into u infinity dy. So you have to use simply this equation. You put the value of u infinity, u by u infinity in this equation, integrate, you will get the relation between the given parameter and delta. So it is very simple. Now we will move to the next topic. Shape factor, it is indicated by capital H. It is the ratio of displacement thickness to the momentum thickness. Shape factor indicated by capital H. It is the ratio of displacement thickness delta star to momentum thickness theta. Now we'll move to the next topic called as drag force. Drag is a force component which is acting parallel to the direction of the motion. So we generally express drag force in terms of drag coefficient, which is the drag force divided by half rho a v square. Similar to drag force, there is a lift force. Lift force is a component of the force acting perpendicular to direction of the motion. It is very important in case of aircraft. In the aircraft, our aim is to increase lift force and to reduce the drag force. So similar to the drag coefficient, there will be the lift coefficient CL. It is given by the lift force divided by half rho a v square. So we'll stop and we'll continue this topic in the next lecture. Thank you. If you have any comments, suggestion, you can write to me. Thank you.